Hi, this is Stephen Jones. I'm going to talk about the second part of regression models. We looked just generally about what regression models are and their explanatory value, and that we need to be careful about what we expect the model is actually saying. So we have to test this model. We left off last time with the mean squared error. We have to test that model to see how well it fits the actual description, how well it fits the assumptions about regression lines, and we have to be sure that there are not alternate methods of trying to explain what relationships are. So the closer that relationship gets to telling a consistent story, I don't want to say the truth, because we don't know what the truth necessarily is. And I'm not talking philosophically. You know, what I'm talking about is how well do the variables seem to fit together to explain each other, and is there a relationship that we think we can use the equation for to help predict or explain one variable by the use of one or more independent variables. So if we start off with the model for significance here and in testing that, we're going to assume that to start off with that there's no relationship. You don't go in assuming that there is. I mean, when you look at it, you say, oh, I think there's a relationship here. You know, I slip, I fall, I hurt my behind. Okay, I think there's a relationship, and I think we could say that that observational relationship is the case. But just because I know that my behind hurts does not mean I slipped and fell. And it doesn't mean that every time I slip and fall, I'm going to hurt my behind. So what we're talking about is, do we have a close enough relationship here where you're reducing the random error that might fall into our calculations? And so we use something called the F statistic to help us know if that relationship is actually a significant relationship. So if the F statistic happens to be very large, that is going to be the case because the amount of error that shows up is very small. If a lot of error, that is randomness that, you know, shows up in the equation, and that line that you draw when you scatter plot these variables, if that line that you draw has a lot of variation of the observations on either side of it, and they don't come that close to the line, then you're going to see an F statistic which is very low, means that there's little or no relationship. But if those scatter plotted observations are actually pretty close to the line that you've drawn, then you're going to see a larger F statistic, and it means that it is excuse me, more likely to have a very strong relationship between the variables, and that the equation does a good job of predicting the dependent variable out there. But you start off saying, I don't know that there's a relationship. That's the null hypothesis, that if you can't prove that the null hypothesis is false, then you have to assume that that's the case. Okay, so we assume that the relationship between x and y is purely random, unless I can prove that that's not the case, unless I can prove that there is a relationship between them, or at least I can prove that the idea that there's not a relationship is probably not the case. Because I might not be able to prove that there is a perfect relationship between them, but I can show that there's not a relationship. I know it sounds weird and convoluted, but that's kind of how we're looking at it. Think of it this way. We don't have to prove somebody is guilty, and we don't have to prove somebody is innocent in a court of law. We simply have to say that the burden of evidence, the burden of proof and the amount of evidence that is brought by the prosecution is such that a reasonable person looking at it would say it is beyond a reasonable doubt that this person did commit it. We still don't necessarily know that they did commit whatever the crime was, but we feel comfortable in being able to say that with a very strong level of certainty, not perfect certainty, but a very strong level of certainty, we believe that this person committed this crime, and therefore we declare them to be guilty. But again, we're not proving that they did, just that they are found guilty of the crime. Just we may not have anything that proves beyond a 100% or a shadow of a doubt. So, we are proving in our situation that the null hypothesis, that there's no relationship, that is essentially something you shouldn't believe in. And that's how we calculate it out. And so if our F statistic is large enough, then we assume that we, in determining that we believe that there is a relationship, that we have a very small chance of being wrong. So, as you look at this, we don't have to calculate this out. Remember, your computer will be able to do this for you. If we show that there is a relationship, a linear relationship between the two variables, we are able to show that because we show that the thought that there's not a linear relationship is incorrect. And in this situation, step 2, they selected an alpha of 0.05. In other words, only 5 times out of 100, if you were to look at this evidence, would you say that there was not a linear relationship? That 95 times out of 100, you would say that there is a linear relationship. You can make it higher. You can make it 0.01, which means that you would be looking for 1 time out of 100 or 1 time out of 1,000. I mean, you can make it very difficult if you choose to. And there are situations where 0.05 is just not good enough. You know, it's just the way it is. If you were allowed 5% of babies to be dropped after they were born, that's just wrong. You would want to have that as a 0, I know. On the other hand, I don't have to feel like I need 1 in a million to be the case when I was looking for somebody to be a friend or to be my spouse. I don't need to be that certain. Yes, it's a forever or a long time kind of a relationship, but sometimes you can be too picky as well. And so that's what we're looking for, is determining the level of pickiness that you want to have in this. Now, what we don't do as people who are analyzing data, we don't get too much more open than the 0.05. We might go with 0.1, but 0.05 is a pretty good standard out there. That means you have a very, very good level of certainty that whatever relationship you're talking about, that you're pretty certain that that exists out there. And so you calculate it out. And the F statistic then can, by looking at the proper table, you can determine what whether or not you hit the alpha that you expected to hit. It also is important that you look for the degrees of freedom. Why? Because the more variables you put into the equation, the less certain you can be about whether or not the relationship is statistically valid, unless you account for that variation. And you can help to account for that by, one, looking at degrees of freedom, and two, looking at the number of observations. So if you have more variables in your equation, whether it's a linear equation or, well, in linear you would just have one independent and one dependent. But if you're looking at multiple regression out there, you need a little more numbers of observations. And in this situation right here, you're looking at improving your ability to say that your equation works correctly based upon having the correct numbers of degrees of freedom. And you can increase that by increasing your n, which is your sample size. So if you have a higher sample size out here, then you have higher degrees of freedom. That helps you to reduce down then the level that you need to have for F. So you can have a lower F bar that you need to get over if you have more observations, up to a point. Once you get past about 30, 40, 50, something along those lines, each new observation really contributes very little because the relationship is either there or it's not. That does not mean you shouldn't have a lot of observations. If you look at the polling that is done, the political polling that's done by organizations, they typically are looking at 1,000, 1,500, 2,000 people asking them questions. But they're doing that because of the variation that happens between people's belief systems, people in different occupations and parts of the country, and so they have to have a broader sample than just 10 or 15 people, because randomly they could choose 10 or 15 that just don't fit. But if you're looking at, say, relationships between stock prices and the Dow Jones or the S&P 500, you don't need that many observations. You need a fair number, but you don't need that many observations to be able to see if there is a relationship between the stocks and the S&P 500 or the Dow Jones. So, as we graph this out then, we would find that we have passed the F statistic bar of 7.71 with the calculated 9.09, and that means that our R squared is definitely significant in that relationship. Analysis of variance looks at the variance between these variables, and we can calculate that with software pretty easily and be able to calculate that F value out there and compare that significance to an alpha. And when you come up with it and you look at the output on Excel, you're going to see an R square right there. You see the multiple R there, the adjusted R square. That's really useful when you've got more than one independent variable, because then it adjusts the R square down for the fact that you're using multiple predictor variables out there. And this right here, the significance of F is related to the F in that this tells us, remember we had an alpha of 0.05, and this 0.0394 is less than that 0.05. So this number right here, the 9.09, is greater than the 7.71 F statistic that we required. And then the significance for F also is lower than the 0.05, which means it is significant. Both of these tell the same story. Our regression coefficients are here, whereas our intercept is 2, and the slope of the line is for x is 1.25, just like we had when we were showing what the regression equation was in an earlier slide. So if you're using Excel to actually do these calculations, you can use the regression option within data. Go to the data tab and go to the data analysis button in there. And when that opens up, you click on the regression line. So go to the data tab. If you have downloaded the data analysis and solver modules within add-ins within Excel, then you can go to data and then over here to data analysis, and when that pops up, click on regression. At that point, then you can put the ranges of data in, and you should have input your data already in there, and you can say, well, this is my Y, sales, and this is my X, payroll. And they have labels, which means that you can click on the sales Y and the payroll X as part of this captured data right there. And then you have to tell it where you want the output, so you would click outside so it doesn't overwrite any other data or text that you may have in there, so you would click on that. And then you essentially just go with OK. And Excel will kick out this table that we were looking at then. So if you're going to do multiple regression analysis, you're going to have more than one independent variable, but you're going to follow a very similar pattern. The difference being that we have to look at a couple more things to be able to see if that relationship is actually a creditable relationship. Now, instead of having just, you still will have the y-intercept here, but you'll have a slope and a predictor and a slope and a predictor, so you're going to have these two having some level of interaction to try to explain your dependent variable out there. And so in this situation, we have a real estate agent who is trying to determine what the selling price for a house ought to be in a marketplace. And one thing that she's looking at is the size of the house, square footage, and how old the house is, age. Now she also has condition out here, but we're going to use these two first, square footage and age. And we'll put those two into the same kind of regression equation. Now what we have here is there are two columns of data for X, because these are going to be in there together. Now this and this are going to be calculated separately, and Excel will look at that. But you will put these two columns side by side of data, highlight them, and then that's what goes into your X range. Your Y range would still be the same single column right over here. You still would have labels right over here, and then you would continue to click on OK. Now what you find is you still have an intercept, just like we had the 2 before and the 1.25. Well, you've got an intercept right here, and then you have the impact that square footage has on sales price and the impact that age has on selling price as well. So essentially you start off with a house price generically of $146,631, and it's affected for every square foot you would add another almost $44, and for every year older that the house gets, you lose about $2,900 in value. And that's really how you would look at this. So starting from an essential point, a y-intercept, where the house has no square feet and it is 0 years of age, so that's where this would buy. A house with 0 square feet and 0 age would sell for almost $147,000. I would like to see that, but that's what the line is essentially saying. We know that's not true, so there'd be a lot of error about a house that's extremely small or a house that's, 2 million square feet if that were to happen. So knowing that that's not going to occur, we know that the range of our data, we would say, because if you go back, notice the square feet are all in numbers that are over 1396, I believe, is the lowest of them. Is that correct? Yeah, 1396. So if we have houses that are about 1,400 square feet to about 3,800 square feet, this equation would seem to fit. Anything that's below that, we don't have data below that, or above 3,800 feet, we don't have data above 3,800 feet. So we really can't talk about that. We can just talk about 1,400 to 3,800. We've got some pretty good ideas of how age and square feet will affect the price of the house. Anyway, so it comes out here. Then you'll notice that this is a pretty low number for significance. The F statistics is high enough, but this significance right here at 0.0022 would tell us essentially that just over 2 times out of 1,000, or 22 times in 10,000 guesses, would we be wrong if we said that there was a relationship here, that there was some explanatory variable here. So we would not be wrong very often by saying those very things. Even though we don't have a good number of observations, we have enough, and the relationship is strong enough to be able to say that. So your R square here is 0.67, and what did we say that said? That the relationship, the change in selling price of the house, 67%, about 67% of the variation in one house to another can largely be explained by looking at the square footprint of the house and how old that house is. And there you go. And that's what exactly we were talking about. So our null hypothesis and we can look at each one of those separately, okay? Well, we can look at them separately, or we can look at them together. Notice the p-value here for each of these two explanatory variables, 0.001 and 0.003. Both of those are very small as well. And as a result, each one separately tells a story, and then the two of them together, the model, tells a story. And that's what we see on this slide right here. Now, dummy or binary variables are used to bring in a situation when you can't really say that you can numerically talk about something. And that's what we were seeing when we saw the good, excellent, and mint conditions in the data. We didn't use that. Go back here. Notice right here in this condition, we didn't have a numerical thing to be able to drop in there. The computer couldn't just look at that and say, well, good, that makes that's a 64.29, and excellent is 79.85, and mint is 98.2, or whatever. Okay, so it doesn't do that. So what you have to do is create what's called a binary or dummy variable to be able to drop in there. So what we would say is the house in excellent condition? If it is, then you get a 1. Otherwise, you put a 0 in. Is the house in mint condition? If you have that's true, then you get a 1, and otherwise a 0. And you might say, well, now wait a minute. Mint condition is better than excellent condition, which is better than good condition. So why don't you just do the mint? Well, because sometimes excellent also is a good indicator. And so if you were to be able to do either one of those, and if a house is excellent, it's not necessarily mint condition. If it's mint condition, it's definitely in excellent condition. But you want to see the strength of either one of those relationships. Good is just a 0-0. So if it's good, it's going to get a 0-0. If it's excellent, it's going to get a 1 and a 0. And if it's in mint condition, it's going to get a 0 and a 1. Now you might say, why didn't I put a 1 and a 1? It was making sense. This is 0-0, that's a 1-0, and that's a 1-1. No. It's not excellent and mint, even though we know that mint condition is better than excellent condition. And that if it's in mint condition, you could have said it's excellent. But we want it to be, was it declared good? Was it declared excellent? Was it declared mint? And you can put all of those together in the X column here, and all the Y's in there. And now you come out and you take a look at the p-values, and notice your p-values on square foot and age have gotten better because you included excellent condition and mint condition. Those two are also both separately significant, and now you've actually improved the value of the overall model because you included more variables. But you do have to be careful because, again, more variables means that you also have more confounding things that might happen. Notice that the significance for the entire model as well has also increased. Okay? And so we've also included some changes in the square foot and the age. So this was a lesser impact for square feet before, and age was also less of an impact on the model than before. But take a look at this. We also now are looking, because it was 140 some thousand as the intercept before, now it's dropped to 120. Why? Because all four of these take on more of the burden. This has less burden because these do a better explanatory job out there. Your coefficient of determination is 0.898, and you probably saw up here your multiple R is 0.9476. What we see here are adjusted R, which we didn't use before. Our adjusted R helps us if we were able to see it. It wasn't showing up on that one. It wasn't showing up on this one because this little balloon here was in the way. But you would use the adjusted R here to modify the 0.898. You would use it to modify that because you'd say, well, you got to be careful because there's so many variables going in. We have to reduce that coefficient of determination, or how much variation is being explained. If we believed that some variables were impacting more than others, we might do what's called a stepwise regression to let Excel or SPSS or some other program tell us which of these had a more explanatory impact. And you would do that with stepwise regression. If you think that all are important together, you just do the enter regression, just regular regression. But you can ask it to put the most important one in first, then the next most important one second, then the next most important one in there. And so what that allows is you can show which variable is having the biggest impact. And you might say, well, it must be like this 47 because that's a big number there. Or it must be one of these two, square feet or age, because the p-values are so small. And it is true that those things are small and important. But that's not exactly how things are going to go down when you do a stepwise regression. You can do a forward or a backward stepwise regression. In any case, if you just do that, you will see with a forward regression, you'll see which one's the most important as you're going into it, and you toss out, potentially you might toss out an extra variable or so, because if the next variable coming into the model doesn't explain enough, then you don't add it in. And all that tells you is you don't have to do observations of that data, that it's just not that important based on all of the others. Something to look for, multicollinearity. If two variables tell the same tale or pretty close to it, then you have multicollinearity. So if you were looking for explanations here, if we were to go back here, if we were looking for explanations, and if in a certain town, and I'm not saying that this relationship exists, I'm just explaining it in case it did, if older homes were smaller because people didn't have as much cleared land to use or as much money to build houses or whatever it is, if older homes were smaller and newer homes were bigger, and we put them into this model here, what you would see is as the home gets older, square foot is going to get smaller, and as they get younger, they're going to get bigger. That relationship right there, though, that relationship between these is not independent. Okay? And because it's not independent, there would be some level of multicollinearity as they try to explain the value of the house. And so you have to be careful about that and look for that kind of relationship if those two variables are not independent. Other things to be careful about besides multicollinearity, you also have what we were talking about before. We only have values of about 1,400 to 3,800 on square feet. So if we were looking at a bigger or smaller house than that and trying to guess it, we can make a guess, but you have to be careful because our model is not intended to look at something outside what we actually were looking at. Correlation does not necessarily mean causation, and you should be very careful about causation out there. Look for relationships, but don't necessarily believe in the concept of causation, or at least that you can explain what causation is. Again, go back, watch those two videos that I have in the discussion assignment. The linear relationship, if you remember the graph that we had where we plotted and it looked like it was an inverted U, looks like it was a hill. A linear relationship is not always the best explanation. Perhaps a better explanation would be that you would look for a nonlinear relationship, that your multiple regression out there is not going to give you a linear, but a quadratic formula, essentially. And then even though the relationship may be statistically significant, they don't have any practical value. If I took a sample of 10,000 M&Ms and I was able to show something, I might get a statistical relationship for whatever it was I showed. But it has very little value when it comes to something else. Or it may show that it's statistically significant, but it only explains 0.1% of why something happens. So it's because I have a lot of observations that I'm able to say something is statistically significant, not because there's actually an important relationship between the variables. Enjoy.